Hi there, my name's Ethan Rosenthal, and today I'm going to be talking about machine learning engineering's arrested development. Basically, why machine learning has failed to mature like some of its sister industries, such as, say, web development or data engineering. If you like what you hear, or if you don't like what you hear, feel free to reach out to me. You can find me on the internet in various places, but I tend to hang out on my personal blog, Blue Sky, and GitHub. To give you a little bit of background into myself and why I'm talking about this today, I want to present you a little history of myself over the last 10 years. So for many people who found themselves in machine learning, let's say 10 years ago, machine learning or data science, a lot of us came from non-traditional backgrounds. So myself, I was a physics grad student, and I had only taken, I guess, one programming class at the time in the math department, and I unfortunately had to learn MATLAB. And so when I got my first job as a data scientist, I was terrified that people would think I was a fraud. People are paying me to write code professionally. And when I would talk to, quote, real software engineers, I definitely had a fair amount of imposter syndrome. And so what I did is I kind of leaned into that, and I spent the last 10 years really trying to kind of find myself in more engineering-focused roles. And as a result, I've kind of moved further and further away from, let's say, the science side of the industry and more towards the engineering side of the industry. And now in my current role, I finally have like the same title as the, quote, real software engineers at my company. And I tell you this to kind of give you an understanding of where I was and where I've come from. And in this talk, I'm going to talk about what I learned along the way. Most of this talk is fairly agnostic to the companies that I've worked at, but if you're interested, these are the companies. But I will say that the current company that I work at, Runway, is a creative technology company where we tend to do a lot of work around generative video and generative images and things like that. And so apologies in advance, but there's going to be a number of these generated images in this talk. And to start off with, I created one to kind of show you where I like to sit in an organization. And I really like to sit kind of right in between the science side of things and the engineering side of things. So the science side of things where we're doing math, computations, scientific programming, and things like that. And then the engineering side where we're actually building things that get used by real people. And so the other thing that likes to often sit at this interface between science and engineering are tools. Tools that are built by vendors, tools that are built by people in open source, as well as tools that are built by platform teams at large organizations. And so for the last 10 years, a lot of tools have been built to try to help to bridge this gap between the scientists, the machine learning scientists, the data scientists, people like that, and the engineers who work to actually productionize this work. So to put these models and analyses in front of end users to have them actually impact the world. And so for the people that build these tools, they often imagine these tools as providing this perfect interface between science and engineering and kind of serving as a conduit to connect these two. But what I will argue in this talk is that actually I feel like many of these tools have formed sort of a barrier between these two ends. And they end up kind of insulating the scientists from the engineers. And that's not great. However, the talk won't only be negative. I'm going to try to give some examples around best practices that I've observed to really help to bridge this gap. But before we get into best practices, let's try to assign some blame. And so there's a lot of people that I think that we can blame for this. We can blame the engineers. So lots of engineers have tried to build these tools for scientists. And what ends up often happening when you have, say, groups of people that sit in different parts of an organization is that we kind of get a manifestation of Conway's Law. So Conway's Law tells us that the systems that get built at an organization tend to reflect the actual organizational structure of that place. And so when you have a platform team that tries to build tools for scientists, what they often do is they build tools that actually separate and resemble the fact that these are two separate teams that are working on this. And what ends up happening, I found, is that these tools can tend to kind of box the scientists in such that they're only able to play within their own little playground. Another key component that I found is that conventional software engineering favors tools and frameworks that are very robust, and you can kind of set them and forget them. In software engineering, we often don't like to change things too often. We're still learning how to do continuous deployment. There's a lot of risk that comes with change. But for scientific work, this work is inherently interactive. We are literally running experiments. And so you want to constantly change what you're doing, and you need that flexibility to iterate on your code. And these two paradigms of kind of rigid software engineering and interactive exploration tend to be at odds with each other. But I won't just blame the engineers, I'll also blame the scientists. So I'm allowed to do this because I used to be one. And so lots of scientists come from backgrounds that, as I've mentioned, that are somewhat non-traditional. Maybe they didn't take a lot of software engineering classes in school. And so we can think of these people as frogs in a well. So there's a classic parable of a frog in a well that thinks that the water that it's in is the largest body of water in the world until until a turtle comes and looks down in the well and tells it, hey, there's a giant ocean out there. And so I literally used to work in a basement in grad school, and so I was both the physical and metaphorical frog in a well, and there was a lot that I didn't know about the world outside of the world that I'd lived in. So I didn't know anything about testing code, let alone how to build a distributed system. And so oftentimes, even if you let the scientists build the tools that they want, they don't necessarily know the right tools to build. And then if you ask them what tools they would like, they often make requests that are maybe good in the short term, but don't have a lot of long-term benefit and are going to incur a lot of technical debt down the road. And so if there's one lesson that I want you to take away from this talk, it's really that all the requirements of software engineering, these are a subset of machine learning engineering. So for all the tools that we build for machine learning engineers, these need to really solve for all of the standard software engineering requirements in addition to the other requirements around iteration and exploration and flexibility and things like that. So that was like a lot of negativity, I would say, a lot of complaints, a lot of blame placed on different people. But I want to turn things a little optimistic now. And I want to look to an example of an adjacent field that has gone through what I would say is a very admirable progression. So back when I started in data science, business intelligence involved a lot of kind of weird GUIs with drag and drop tools that allowed people to build connectors between different data sources and build out data pipelines and things like that. But the people that were working in this field didn't get to enjoy all of the benefits of a modern software engineering workflow. However, nowadays we have analytics engineering, where we now have people that are building out data pipelines and doing data engineering, and they're able to enjoy writing actual code, committing that code to GitHub such that they can collaborate with other people. We now have tests. You can run tests against your dbt models. You can continuously deploy new prefect flows. And this field has really progressed quite a bit in the last 10 years, such that I'm pretty jealous of it. And I think that we can see the same type of things happen with machine learning engineering if we start to actually solve for a number of the issues that I'm talking about in this talk. So that was kind of a big overview, and I'd like to start to dive in and be a bit more specific around different examples in the life cycle of a machine learning engineer in terms of anti-patterns that I've seen, as well as actionable advice on how to improve things. And so a very simplified life cycle of a machine learning engineer involves first doing exploratory data analysis, which is basically just slicing and dicing your data, calculating some metrics, visualizing your data, and getting comfortable with it. After you've done that and you feel confident that your data is clean and perhaps could be used to train a model, you then step over to model training. And in model training, we're typically training a model to predict something. So maybe we are predicting whether or not an email is a spam email. Maybe we're predicting the next word in a sentence using an extremely large language model. After we have trained the model and we feel that it is good at predicting things, then we typically have to deploy our model. And this is often called model serving or model inference, but the idea here is to kind of get the model to generate predictions and put these either in front of users or have these drive automated decisions. And so this is often done as maybe a batch job, or maybe we're classifying emails via a real-time API. And so let's go ahead and start with the analysis side of things. And I'm going to walk you through a story that I call Notebooks in the Cloud. So I worked at a company where a lot of the data scientists and machine learning engineers like to run analyses, analyze their data, and even train their models in Jupyter Notebooks. And at the time, they needed larger machines to perform this analysis on, and they also were not allowed to analyze some of the data on their personal laptops. And so they made a request to the platform team to build them a service to be able to run their notebooks in the cloud on larger machines. And so the platform team went out and they did that. They built this service where a data scientist could kind of log in and they could run their notebook in the cloud. And this service became kind of a little sandbox for the data scientists to play within. And it had a lot of far-reaching implications. And notably, in this service that was built, there was no access to GitHub that was provided for a number of years. And so, just with this kind of small tool set, we end up seeing a whole bunch of downstream effects that happen. So firstly, if you make people's development environment only involve notebooks, then that's all that they are ever going to use. And so as a result, a lot of the data scientists were not able to kind of extend beyond Jupyter Notebooks. They weren't able to easily reuse their code. They weren't able to build out Python packages and learn about writing tests and things like that. Because they lacked access to GitHub, nobody ever saw each other's code. Sometimes people would maybe upload some of their code to CloudStorage somewhere and point somebody else to it, or they would maybe email their code to people. But when nobody is making their code public, nobody can learn from each other. And I've always found that code review and kind of public code ends up being one of the best ways to learn and develop as an engineer. For the people that really did want access to GitHub and did want to try to have that workflow, they had to develop very weird development DAGs, I'll call them. So I remember uploading my code from the notebook to CloudStorage, downloading it onto my laptop, and then pushing it up to GitHub. And this whole process was certainly suboptimal. And all of these things end up adding up into arrested development, both in terms of the professional development of the people working there, as well as what they're actually building. And so my recommendations for scenarios like this are that, firstly, this is going to be a theme throughout the talk, but if you're building out a development environment for people, even if they're in, let's say, a slightly adjacent field to software engineering, we need to solve for all of the requirements of conventional software engineers. And so we need to give these people a full development environment. We need to give them full access to their IDE of choice and things like that. I am sympathetic that oftentimes people like to work in notebooks, and maybe they have a lot of one-off analyses that they're running, which do often fit very well in notebooks. And so they may not feel the need to go through all of the friction that is GitHub. But again, I think an issue here is when nobody else is seeing each other's code, nobody's learning, nobody's reusing anything. And so a good pattern that I found, if you find yourself in this situation, is to create a fire and forget repository. And so what I mean by that is create a single GitHub repo, give everybody on the team their own directory, and let everybody just push directly to the main branch within their own directory. Nobody's going to clobber over each other. Everybody backs up their code this way, and everybody's able to also see each other's code and learn from it. And then maybe as people start to get comfortable with this setup, maybe they start to build out libraries with reusable functions and things like that. Okay, so let's say that we have moved beyond our arrested development of only working in a notebook, and we've learned how to build Python packages and everything else. And maybe to start out with, we're doing this work on our own laptop, and we're just trying to train a machine learning model locally on our laptop. If you're having a really good time, you might have code that looks like this. You might have actually built out an entire Python package with multiple Python files to organize your code. Maybe you've written tests for your code. Maybe you're using a dependency manager. Ideally, it's UV. Maybe you have your own custom Docker image so that you can manage situations involving CUDA and GPUs versus your Python dependencies. And maybe you even have various entry points within your Python package for calling code from the command line. And so let's say that you've built this all out. You have your tests, you have your entire development workflow, you have CI/CD set up and things like that. And now you want to graduate beyond running code on your laptop, and maybe you need to now train your model in the cloud. So this is often where there's this inherent difficulty with machine learning, which is that we typically have to start involving the cloud or other people's machines in order to train models, because models often require large amounts of RAM, they might require GPUs, you may need large amounts of parallelization and things like that. And once we start mixing code and infrastructure, things get hairy. And so let's say you want to do this, and so you decide to reach for one of the many frameworks out there that allows you to run machine learning jobs in the cloud. Unfortunately, what you often find yourself with is something like this. Maybe you need to learn this framework's custom YAML schema because that is the only way that you can actually configure your job in the cloud. Maybe these frameworks assume that you only have a single Python file that you're running. They don't have any support for a local Python package. Maybe they use their own proprietary Docker image, and so you have no control over that. And then on top of that, maybe you don't get to use your own dependency manager, and instead you now have to redefine all of your Python dependencies manually within this config. They might have their own proprietary runner for running your code, which doesn't allow you to use your own entry points that you're used to. And then worst of all is sometimes they have an entire domain-specific language that they've built on top of YAML for configuring everything. And so that's not a great situation, because now you have to decide, do I want to refactor everything that I've done in order to use one of these frameworks? And that's painful. But let's say that you decide that, yes, you're going to go through all of that effort because infrastructure is difficult and things like that. What often ends up happening is that a number of these tools that exist out there, and I don't want to name names or anything, a number of them often assume that you are running a job in the cloud. And what I mean by job is something like a batch job. So maybe a job that you're going to run once a night, maybe a job that you want to be able to set it and forget it or something like that. But oftentimes these jobs that are supported are not necessarily organized around an interactive workflow. And so now if you want that interactivity, maybe you need to go back to your notebooks in the cloud, or maybe you need to have this slow job. And so the idea of having to choose between going back to notebooks or waiting 20 minutes for your job to start up is not great. And neither of these are a good scenario. But let's say that you bite the bullet and you decide to go with the job with the 20-minute latency, and now you need to start to schedule this job, and maybe you need to start to orchestrate some parts to it. I'm sure some of you have seen DAGs that look like this workflow. Sometimes these DAGs often also involve like using Jinja templating and other sorts of things. And when I worked at one of the companies that was in my slides earlier, we did find ourselves with DAGs like this, but we kind of wanted an interactive workflow with them. But that tended to be difficult to program this. And so what most people did was they would take the entire DAG and they would shove it inside of a single DAG or a single operator in this framework. And this ends up kind of being the worst of both worlds. And so that certainly feels like an anti-pattern. And so at the end of the day, all we want to do is be able to just get back to that situation that we had with our local code, where we're just writing Python code, and whatever we're doing on our laptop, we're also doing in the cloud. And so I would argue that there is a better way than a lot of these frameworks and tools that exist, or a lot of things that platform teams build. And so this is a point that I'm going to keep hammering, but core to all of this is that you need to make sure that running interactive code is placed on is given the exact same weight as reproducible and robust jobs and orchestration and things like that. And so that need for interactivity is quite crucial here. Another thing that I've found is that with all of these different frameworks, these are frameworks, and there's a pretty large onboarding cost to them quite often. And especially if you then have to refactor all of your code in order to use one of these frameworks. And so I really like the idea of being able to progressively onboard to a tool. I think Prefect actually does a great job of this, but you've probably heard a lot about Prefect today. And so I'll talk about a different tool briefly, which is called Typer. It's a Python package for building command line interfaces. And everything here is ripped straight from their docs. But the idea is that you can get started very easily. So all you need to do is call a single function in order to start to get a little bit of a nice command line interface built on your code. But then if you find that you like the tool, and you see here you don't have to refactor your code very much in order to use it, maybe you want to start to add a couple commands to your command line interface. It's only a couple decorators that you need to add. And it's not until you've decided that you're really invested in this tool that you can make your code start to look fairly complicated, such that maybe it only makes sense to a user of that tool. But being able to quickly get onboarded and not have to refactor your code ends up being crucial. And all of this kind of gets back to this idea that when I'm working on my code locally, there's a bunch of features of what I'm doing that I don't want to have to change. So these should all be invariants of your workflow in terms of I shouldn't have to change any of these things when I go from working locally to deploying code in the cloud. And so it sounds kind of boring, but what I've found to be the best way to make sure that all of these requirements are met is to just use Docker, subject to heavy investment in caching. And so if you have a Docker container, you actually have control over your package structure, your entry point, all of your dependencies, your tests. All of this can match your local development environment as well as what you're running in the cloud. The only issue is that if you don't heavily invest in your caching logic, then you might find yourself waiting 20 minutes to upload a very heavy Docker container from your laptop that contains CUDA and PyTorch and a bunch of other things. But I've now worked at 2 different companies where this is our very boring workflow for both interactively training models as well as scheduling model jobs and things like that. And it's at the core, it's just Docker and caching. We've used Kubernetes, we've used AWS Batch. You have to find a way to run the Docker container in the cloud. But at the core, it's just Docker and caching. OK, so let's say you've taken all of my advice, and you have now trained your model using Docker and caching. Now you need to deploy this model somewhere, and you need to get it in front of some users. And what I've often seen as the way that this gets implemented, especially at larger companies, is this idea of throwing the artifact over the wall. So this is, again, kind of an example of Conway's law, where it becomes the job of the data scientists or the machine learning engineers to just train a model, and as long as they can serialize it to some file format, then they can hand that artifact off to the platform team. The platform team says, great, we will get your model deployed with high availability behind some real-time APIs. And while that sounds nice in theory, and it's certainly nice for, in some ways it's nice for either side because we have a separation concerns here and things like that, we often run into some issues. And so in order to kind of illustrate an issue that we might have here, I'm going to walk you through a real example from my time when I was at Square. So when I was at Square, I worked on a team where we built a tool for businesses where customers could text, message, or email the businesses, and the businesses could respond to them over text or email. And my team worked on training large language models, pre-ChatGPT, to be able to suggest responses for the business owner to send back. And so an example of this is maybe Jane Sanders sends a message to the business just letting them know, wow, that was the best $30 steak I've ever had, thanks. And then we can suggest a response for the business to send back. Maybe we suggest for them to say, I'm glad you enjoyed the steak, Jane. Come visit us again soon. And the business owner is free to use our response, save a little bit of time, or they can write their own. And so at the core, it looks like, oh, we have this model artifact in the center that was handed off, and we're good to go. But alas, within that model, there's always more models. At the end of the day, a model is actually a series of decisions that get made between an input and an output. And some of that might involve deep learning and machine learning, but some of it might just be business logic. And so for us, as kind of a basic example of this model, we had 3 steps. First, we needed to validate the text that was sent in. there's certain information that we didn't want to feed into the model. So, we would redact phone numbers, we'd redact credit card numbers that people would send, and we also even didn't want our model to know exact dollar amounts for things. And so first we have to run that redaction. We then actually run, our fairly standard language model in order to generate the response, but then we need to validate that response afterward. And so the example that I'm showing here is that we need to make sure that when the model generates a name, it's using a name that is actually relevant in this situation and not a name that it has maybe hallucinated. And so maybe we now need to layer other models on here, and we need to run some natural language processing model in order to extract names from the text and then cross-reference those in a fuzzy manner with auxiliary information that we have. And then finally, once our response has been validated, we can send it back. And so what you see here is that our model is not just kind of a single artifact of weights and biases. Instead, it's a combination of that and business logic and potentially other models. And so oftentimes, when you start to look at what tools are out there for handling a situation like that, they kind of follow at least the top 3 lines of this galaxy brain meme, where, to start off with, we have, a pickle file that the tool is asking us to hand off to them, and that's not going to really handle all of this complicated business logic where we maybe need to even connect to other data sources and things like that. If you end up looking beyond this, you might find tools that say, okay, we don't just take a pickle file, but you can actually also hand us a script to go along with it, maybe an inference.py script. But here we have all sorts of natural language processing code that we're working with. All of this exists within maybe an internal library of tools, and that's not all going to fit inside of a single Python script. And so then moving beyond that, maybe the tools say, sure, actually you can zip up arbitrary Python code into the same zip file that also contains the model, but actually in our scenario, we might have certain Python dependencies that are important, and we need to version things, and none of this ends up being very satisfactory. And I'm gonna have a common refrain here, but all I want is to just run my code in my container. And so you might ask yourself, I now have kind of the same requirement for both training the model as well as serving the model. And so this often feels somewhat antithetical to a lot of software engineers, but really what I think the best way to solve for all of this is to just have one giant repo that does everything for you. So it feels bad, we just came off of like 10 years of microservices and things like that, but one big monorepo is how things have worked at a number of the companies that I've worked at. I've also worked at companies that invested heavily in microservices for machine learning. And what I found is just having one big repo where you put all of your code for both training and serving, and even sharing that code between the two ends up just working out very well and allows teams to move quite quickly. And so if you now start to take a step back and view our machine learning lifecycle from this viewpoint, where we now have one big repo where we run all of our code from, what this allows you to do is it allows you to start looking at how your model actually gets used in the real world. And it allows you to start to actually analyze the outputs of the model. And maybe you start to look at, well, how are we parsing out people's names from those responses? And maybe you find that your model, your parsing logic is good for American sounding names, but it's not good for other names. And you find that actually if you improve the parsing logic there, then you're actually able to improve the model, which then improves downstream business use cases. And now that you have all of your code in one place, you can actually start to use that code that you're using in inference in your own analyses to look back at the model. And you start to create this actual flywheel effect, which, as we all know, flywheels just print money, and that's what gets the VCs salivating. Let me know if you end up doing this yourself, but I just want to thank you for your time, and if you're interested in talking about any of this, feel free to reach out to me at my website. And P.S., if you're interested in a new job, Runway is hiring, and I would also say that it's probably the best development environment that I've worked in yet. Thank you.